So our next speaker is Volker Krause, who will take us to Middle Earth, I think, into the land of elves and dwarfs, or maybe not.
Okay, thanks, Martin. Yeah, not exactly. We are going to talk about binary formats, so the files that the compiler and especially the linker usually produces for us. That's files we usually don't interact with much besides actually running them. So usually we look either at the code or we look at what the application is doing at runtime, but not so much about what we have as an intermediate state there. But there is actually a number of interesting information we can find in those files and a number of interesting problems where it's useful to look in those files. It starts with simple stuff like linker errors that you might encounter every day, problems with loading plugins, all kinds of optimization questions, and also some very nasty runtime issues where you have behavior that you can't really explain because the code triggering that behavior is actually generated by the linker and you have no chance of actually seeing this in the debugger. This was originally a talk for an hour-long slot, and then it was shortened to half an hour, so we will only have time to look at a handful of use cases and the tools available to deal with them. So we will need to take a few shortcuts when it comes to the in-depth technical details, unfortunately. Just as a very coarse overview on what you typically find in those binary files, while I mainly focus on ELF, so the format you find on Linux, most of the concepts are also applicable to Mac O on Mac and PE on Windows. The data in those files is usually split in a number of segments that are memory mapped at runtime. Usually you have at least three, one for read-only data, such as string constants, one read-only executable, that's the actual code. Those two sections are shared between all applications that use the same library, and they are only loaded into memory on demand. So if you have a large amount of code that is only used in one specific corner case, that won't impact runtime performance, for example. That's different for the read-writable segments. This is stuff like memory that is kind of globally allocated, global variables, but also structures that are simply needed for dealing with dynamic libraries like read tables. This isn't shared, so this is kind of the off-the-shelf memory consumption of a library you are using. So this is something you want to reduce. Then you find in there the symbol table. So this is basically just a mapping from a textual representation, basically the function name you have in code, to a memory address. And then there's the global offset table and the procedure linkage table. That's basically an empty shell in the file that is filled at runtime, and that's necessary infrastructure to interact with code or data from a different library. And there's debugging information. That's typically read-only data, so that has no impact on runtime. If you have been to any of Milian's talks, he's always advocating to build in release mode with debug information, and that's fine because the release mode only affects your code and optimizes that. The debug information is just extra stuff tagged onto the binary file that doesn't really impact runtime. It just gives you ways to map code location or memory addresses back to source code. Of course, this goes into way more detail if you would have the time for it. But that is enough for the following use cases. So let's start with linker errors. This is probably something you run into every day. Unresolved symbol, blah, blah, blah. And the compiler stops there and doesn't generate your executable or DLL. I mean, the first things you do there is you look at the code, you see if the function is actually defined, or you look for a number of typical reasons for this, like mock not being rerun and the read table is missing. But sometimes that doesn't really help, and you still have the error and can't explain it. And then it's useful to be able to look into the files and see if the symbols are actually there and if they're exported, so if they are publicly usable. Reasons for why that might differ from what you see in code is you have outdated header files installed or an outdated library, or your linker picks up an outdated version. And you can verify that on GCC or Clang-based tool chains with NM, readelf, or object dump. Readelf and object dump are fairly generic, so you can access all kinds of elf details with them. NM is dedicated for listing the symbol table, so this is usually more convenient for this. By default, all of those tools will give you mangled symbol names. So since we are all working with C++, if we are using Qt, you have stuff like _z, and then, well, you vaguely see some class names in there, but it's very hard to read. There is a tool to demangle that C++ filter, so you can just pipe through the output through that, and you get normal readable C++ names. And all of them also indicate you if the symbol is exported or not. So with that, you can at least verify, does your DLL match what you see in the code. The counterpart for that on Windows is Dependency Walker. That is a UI tool with a lot more features in it, but it serves the same purpose. So something slightly more interesting, loading errors. Might happen when you start an executable and one dependent library isn't found. More common, you see this with plugins. So you have the Qt plugin system, you try to load a plugin, and it fails. For that, there is a number of things. Oh no, plugins we actually get later. So this is just for the libraries, sorry. For that, we need to know where the loader actually looks for libraries. There's a number of system default paths, and then there's a number of environment variables that adds extra search path. This is LD library path on Linux, DY library path on Mac, I think, and the regular path on Windows. On Linux and Mac, you have the additional concept of rpath. That's basically a compiled-in search path in the library. And the linker will look into that as well. And you see already this is getting kind of complicated, so there's lots of options where to look for the library. It would be good if we can actually see what we will get in the end when running our executable. For that, we have LDD on Linux, OTool on Mac, and again, Dependency Walker on Windows. So this is basically, this emulates the same search algorithm that the linker would perform, and it gives us a list of all libraries that, without executing the program, that would be loaded in the end, and the absolute path to them. So this basically tells us what will happen at runtime. It doesn't really help us yet with the why. The next two tools here, readelf-d and otool-l, those will help us to look at the compiled-in search path, because that is, everything else is fairly easy to see, right? We can look at the environment variables, we can look at the system settings, but looking into the binary to see what extra search paths that will add very often already explains the reason why we get a specific DLL loaded. And then we have two more options to look at at runtime on where it's actually looking for libraries. There is the LD debug environment variable, and with that the runtime linker will print out all the search path where it's looking for. If it finds a candidate, why it's not using that candidate, might be a different architecture or whatever. So this gives us a fairly detailed insight in where stuff is searched and why or why not it's loaded. And you can do something similar with strace, which basically shows you all the file operations, including that of the loader. And you'll see where it actually tries to find the library. Right, and now we get to plugins. Plugins are similar in that extent, right? It's a DLL reload at runtime. So the same applies as we saw earlier. If a dependency of the plugin DLL isn't found, we can apply the same tools we have just seen. But there's a few more information in plugins that could cause problems. Qt plugins can have metadata attached. By default, that is the Qt version they were built for and the Qt configuration, so debug or release builds. On Linux, that is, I mean, especially the debug release part is ignored. On Windows, this is actually very relevant. Qt will reject any plugin that doesn't really match the same configuration of the host tool. So this is one of the things to check if your plugin isn't being loaded. This metadata is actually encoded in a separate section in the DLL. So it's raw binary data. The way to easily decode this is Qt plugin info. That's a small command line tool that was added in Qt 5.5, and that allows you to dump out the decoded JSON that is actually in that section, and that contains the Qt version, the configuration of the build. And if you use that additional custom metadata, that might influence if your application is loading the plugin or not. That's something that is very common in the KDE libraries, for example. If that doesn't give you any information, you can check with readelf sections if the Qt metadata section is present at all. If it isn't, then probably something is wrong with your plugin and that's not compiled correctly. Same as if the entry point in the plugin is missing, Qt plugin instance. That's also an indication that you probably missed the Qt plugin macro and you have a DLL, but it's not a valid plugin. And if that still doesn't load, check if all the dependencies are found with the means we saw in the previous section. Oh yeah, and now we get to my favorite in this. The cases we have seen so far are, well, more or less straightforward, right? It's, yeah, tiny things missing in the build, some information missing in the DLL, some DLL not being in the right place. This is now about subtle runtime problems that can happen in some hopefully exotic toolchain configurations. We have actually encountered that twice in real-world projects now, and that goes back to linker-generated code. So if we look at this very small example here. Looks completely harmless. What happens under some circumstances, so I don't want to scare you from using the new static connects. Most of the time they work. Just if they don't, it gets a bit tricky. So this is the code, and this connect fails at runtime because it can't find this signal. And if you look at the code, this makes absolutely no sense, right? The QBuffer is an I/O device that has ready read, right? This compiles, so the function pointer is found, it's passed in, but it still can't find the signal. The way the signal lookup works is the meta object has the function pointers for all the signals in its data structure, and it compares with whatever you pass in here. And if it's found, then the connect succeeds. If it doesn't, well, then the connect fails. So this is weird enough, right? This shouldn't fail at all. But it gets better. So if you remove this call to ready read here, or the emission of the ready read signal, it starts to work. Also, if I break here, so before this is even executed, it still fails, right? So the code pass that executes it is after I actually use it. So what happens here is that we actually end up with two different function pointers because the pure presence of the ready read usage in a different DLL here generates a PLT entry, so the kind of like a small local jump function to the actual function in QtCore. And if your toolchain is buggy or configured wrongly, we will get the function pointer to this PLT function here, and QtCore uses its own local address, compares the two, and they are of course different. And then the connect fails. And in order to trigger this, I just need the presence of the same function call here to emit this. I don't even need to call it. And all of that happens in linker code, so you can't actually see it if you step through it in a debugger, because that will skip all the auto-generated code. The way we found that in the end is looking at the relocation entries in the binary, which you can do with readelf again. But again, this in a normal setup, this shouldn't happen. And the newer Qts have actually safety measures against misconfigured toolchains. So you get actually a compile error telling you, please use the position independent code flag pick in order to prevent this. We have seen this twice so far in the real world. One is with a wide range of GCC toolchains on ARM. So anything up to 4.7 or 4.8 was affected on all ARM systems. And we saw it with GCC5 also on x86. On ARM initially it was considered a bin utils bug and fixed there, but with GCC5 apparently that was the intended behavior. And as response to that, Qt actually adds the safety measures. So if you see something like that and you're sure your code is correct, verify that those settings are correctly set. Position independent code for everything is the one you need. But yeah, this is basically an example on where in a real world Qt application you can hit problems that you basically can only debug on the binary level. Going into detail what exactly happens there probably would fill the entire talk, so we have to continue here. Right, there's also performance aspects where looking at the binary file is quite useful. Memory consumption for once. As I mentioned earlier, we have read-writable sections that aren't shared, that are basically always allocated once you use a specific DLL. In order to visualize that, there is a tool called Elf Dissector from KDE. This basically gives you a tree map of symbols and the amount of memory they need. The color coding here is relocation density. So red means it's full of relocations, which is even more expensive. So that's parts you want to optimize away. We are looking at Qt widgets here, and the bluely marked areas are conceptually constant XPM fallback icons for widget styles. And this is a perfect example of what you don't want to see in read-write memory, because it's constant, right? So it shouldn't show up there. But the way it's implemented is an array of const char pointers, and pointers are changeable and need to be relocated. So that's why it's red and showing up in read-write memory. So this is something where you want to change data structures and formats, especially for something like a fallback icon. You don't want to load that every time you load your DLL. So that's also stuff you can find by looking at the binary files. Another thing is the memory layout of structures. And you probably know the rule of thumb on order your member variables by alignment in order to avoid gaps in between. I mean, this is true in general, but if you look at slightly more complex C++ structures, like the example above here, it's not that simple. Q shared data, for example, that is a common base class if you do implicitly shared value classes. That has a size of 4 bytes. Assuming this is an 8-byte alignment architecture, this actually has like 30% padding, 30% loss in memory. If we would change the member variables, taking into account knowledge about the Qt base classes, we would save those 30%. So if this is a high volume value class, that is actually quite significant. And that's information you can extract from the debug information, because the debugger needs to know the exact memory layout in order to show you the values at runtime when you are debugging. And again, there is a number of tools that can do this. The Elf pack check part of Elf Dissector is the one that seems to work best with C++ classes. It fails on virtual inheritance. The other two, the payhole from DWARFs, that seems to work great with mostly with C data structures, but fails on some C++ constructs. And the GCC flag for padding, that is just way too noisy, unless you have very strict requirements there. Okay, one last thing. I'm not sure if we have time for that, so very quickly. GDB is, when attaching to a program, often very, very slow because it has to parse a huge amount of debug information. Combining some of the binary tools, you can actually put an index for GDB into your DLL that makes it 5 to 10 times faster. I published the slides with the exact command for this and a script that does this on basically from a whole folder of DLLs to get the maximum effect. That will be next to the slides. Yeah, I think that's all we have time for, right? Okay. Any questions? Right. So the question was, how do you fix const char arrays to not need read-write memory and need relocations? I mean, if you just have one string, just making it a const char array rather than a const char pointer avoids the relocation. If you have an array of arrays, what you need is something like the string table that mock generates. So you have basically one big string that contains all the data and just have indices into this. There is a blog series from Mark Mutz on how to do this with preprocessor metaprogramming magic. It's fairly complicated, but very easy to use in the end. And that generates your data structures that are completely relocation-free. So that saves memory and that saves startup time. Yep. Okay, so the question is about tools for binary compatibility checking. There is static tools out there that verify if binary compatibility changed from one DLL version to the next. I'm not aware of something that can check binary compatibility requirements for a plugin. The problem is, I mean, there's two things affecting this. One is making sure that the necessary symbols are available. That is fairly easy because it's basically just string lookup in the symbol table. The more tricky part is that the memory layout of data structures is also part of the ABI, and that you would actually need to check by comparing the debugging information to see if the offsets to, say, a QString member in a structure is in the right place, because your plugin will have the offset compiled in the actual code, so you have no way of checking if that changed. So just looking at the DLLs, it's DLLs without debug information, I would say it's almost impossible to guarantee statically that the ABI is compatible. With debug information, you might have a chance. What you probably want to do instead is to have some sort of version number built into your plugin. Yeah. Yeah, I mean, what you could do is use the API that your plugin uses and run the ABI checkers against that. But then you need to keep an old version around, basically, of all the headers and check if any memory information changed. So it's a lot of effort. It's done for tools like Qt, but doing it for your own custom plugins, just auto-incrementing the version number might be easier and might be good enough. So. Yep. For Windows, I am not aware of one. You probably find them. I mean, there's two places where you can find the memory layout. One is the compiler, because that needs to know it as well. And one is in the binary file. The compiler would probably, well, both have the problem that there might be defines that change the layout. So that's a bit tricky. But I mean, the GCC flag, that should work with MingW on Windows as well. But as I said, that gives you noise for every padding, while the ELF packcheck tool, that only gives you avoidable padding. But I'm not aware of something like that for Windows. Yep. Okay, so the question is if this is also doable with cross-compilation. And yes, your typical GCC cross-compilation toolchain has all those tools included as well. And then you need to use those. So you need LDD or NM from the toolchain. And then you can examine, for example, your ARM binary on an x86. So that works. Any other question? Yep.
If you have like one error, you want to determine how it is.
So you mean to find the function it's looking for?
Yeah, like how it is searching.
Well, The way it's actually searching is there's hash tables compiled in to make the lookup extremely fast. If those are broken and the symbol is actually there, I'm not aware of any tool that does sanity checking in there. But that would be a really nasty linker bug. I mean, you can use NM to just get a complete list of everything that's in there and look for the symbol. I mean, that's the usual workflow, right? The linker tells you, I can't find the symbol. You look at your code. You think it's there, right? It's exported and looks all correct. And then you can look at the DLL, list all the symbols, filter it for the one you're looking for. And I mean, then there's 3 possible outcomes. Either it's there and exported, so the linker shouldn't complain, and it's probably picking up the wrong library. It's there and not exported, then you know what to do, right? You need to make sure it's exported. Or it's not there at all, then it might be you might be looking at the wrong library, or your header might not match the DLL, or you just forgot to link it to something, yeah. Okay, Martin says stop. So if you have more questions, I'll be upstairs at the KDAB booth for the rest of the day. Thank you.